Um, Welcome back from the holiday. I hope you enjoyed the holiday. So, actually, on the information given to us, it was said that we are to have a revision today. But since like 2 days now, I've been preparing for the slides for the topic we are supposed to treat next. So, permit me to let's go straight to the class for today. And the topic we are treating is simple machines. Simple machines. I'm sure we have heard of that topic before. Um, to me, I have seen students not really complaining much about the simple machine because it's straightforward. It's just that one or two part of it is usually confusing. So I want to assume that the way we will have the class today, we shouldn't have much challenge, but we may have challenge in some of the tough calculations therein, which we may not treat today because of the time. We'll continue the next class. All right, let me quickly share the slide and start the class immediately. Um, I need the admin to help me allow that I share slide. It's saying host disabled attendance screen sharing. Can you do that for me, Mr. Abdullah?
Sure.
So while we are waiting for that correction, I'd like to I would like to see the students giving one or two comments about how they are interested in what they are going to have today. How excited are you? Are you expecting something new, or it may probably be what you have heard of? Please kindly send a message on the chat page for me to know how excited you are about this class. I'm sure you are going to enjoy a lot from it, but I just want to hear your comments
Try
so
to
I
share
can.
screen also.
All right, no problem. Thank you. Okay. Um, okay, that's the material. That's the slide. Slide is talking about simple machine. It's a 27 slide presentation. So, but I am very sure to make it interesting, I had to put a lot of pictures so that you would enjoy some of them. It doesn't have to be story all the time. So, um, like I said, please, I need you to pass a message on the comment page or the chat page so that I would be sure that you are following me. Kindly do that before we commence. Okay. All right. So the topic, like I said, is simple machine. Simple machine. So when you hear simple machine, what comes to your mind? What's the simplest definition you can give for a simple machine? Anyone, please? Yes. Please, I need definition. What do you know about simple machine? If you are asked to define in simple terms, what is simple machine? Okay. Nobody is responding. I needed to be sure that we are all here so that I will not just be talking. Okay, thank you. Someone just responded.
Yes.
Okay, someone said a simple machine is used to carry out simple operations. Well, we can actually use a simple machine to carry out complex operation too. You can have two, three, four, five simple machine carrying out a complex operation at the same time. So any other definition? Last one. You should be able to give a very simple definition. How many of us have watched the film Three Idiots? If you have watched the film Three Idiots, you see how that I think Rancho defined simple machine. Very simple term. If you can remember that, that is the best definition you can give for a simple machine. So for us not to waste our time, a simple machine is any device that makes work easier. That is just it. That's the simple definition. So before we go to that quickly, let's look at the objective of this our class. The first one, by the end of the class, all of us should be able to define machine with their examples, should be able to define sometimes related to machine as we have it there. Now, what we are used to is mechanical advantage, but another word for mechanical advantage is force ratio. Then we should be able to define velocity ratio, efficiency, work input, work output, load, effort, and the likes. Then we should be able to mention the 7 simple machines. There are actually many machines, but the simplest one are the one we call simple machine, and there are actually 7 of them. Then under that simple machine, we have the lever. So we should be able to mention the classes or the types of lever with their examples. Then the formula for velocity ratio in the different types of the simple machine, and to solve some calculations. So like I said earlier, the definition of a machine is what I've just given over there. Very simple. A machine is any device that makes work easier. That is the simplest definition. But if you want to be a bit more specific, we have that shows a force applied at to overcome a resisting force at another point, right? So that is the definition. Please look at it very well. I'm just trying to conserve our time. By the time we are looking at some of the diagram, we may be able to explain better what we are trying to see here. But in simple term, what we are saying in essence is all machines generally have 2 points. The point of where the load is supposed to be, where you are going to exhibit the work you want to do by carrying a load or something, and the other side is where you are applying a force so that that work can be done, which is the point that we call the effort. So some other machines may not show us the fulcrum, but most of them also show. But majorly, we always talk about the force, I mean the load and the effort, right? So going to the next slide, um, we quickly go straight to the terms that we have in machine. You can see the terms that we have written there. We have load, we have effort, we have mechanical advantage, we have the velocity ratio. At the next slide, we have work input, work output, and efficiency. So you can see that definition. Those definitions are there for you to see. It says load is the force or resistance that must be overcome by the machine. Effort is the force applied to the machine to do the work. Mechanical advantage is the ratio of the load to effort. All those ones, I'm very sure it's very clear to you. I don't think you should have problem with that. It has no unit. Mechanical advantage and velocity ratio, because they are ratio, they do not have units, right? That is clear. The next slide talks about work impute. Now, you need to look at the way I underlined, I mean, those points that I underlined in the definition. I said work impute is the amount of work done on the machine. So that is the point where you are putting in when you are putting in something, you are putting in a particular kind of energy. Now, I made a mistake there. I said it has no unit. It actually has unit. The unit is joules.
Sorry, we can't hear you again.
Please, sir, come again, sir. Come again, sir.
I think it's his network. Let's just hold on for him.
Impute and work output. It's important you understand what I'm saying there, because when questions start coming up, sometimes the question will ask you to find work output. They say you should find work input. So if you understand that work input is talking about work done on the machine, which is like the effort and the distance moved by effort, you'll be able to understand that this is what you are asked to solve. So that's why I'm laying more emphasis on that aspect. So that is that about work input and work output. Then we have the efficiency of the machine. The efficiency of the machine is defined as the ratio of the work done by the machine, that is work output, to the work done on the machine. Admin, kindly enable the slide again, please. So while we wait for the admin, please listen to what I'm about to say, and I want you to try it. Most of the times, students have been asked to prove it. Some of us can do it. Some of us couldn't. So some of us couldn't do it. So and it's a common question in WAEC. Almost all the time it's coming out. So if work input is effort times distance moved by effort, and work output is load times distance moved by load, and efficiency is work output over work, show that the efficiency of a machine is equals to the mechanical time. Please, I'll just give you like 3 minutes. I think I hope 3 minutes is not too much. That's like 180 seconds. So I really wish to see someone that will be able to work that thing out. It's something that is always common in your WAEC exam. Let me repeat. We know that the mechanical advantage is load over effort. And we have also seen that the velocity ratio is distance moved by effort over the distance moved by load times 100, no times, distance moved by effort over distance moved by load. And we also know that the work input is effort times distance moved by effort. And we also know that work output is load times distance moved by load. If all those formulas have been given to you now, prove that the efficiency of a machine is equal to the mechanical advantage over the velocity ratio times 100%. Knowing that the definition of efficiency is work output over work input times 100%. 3 minutes. Someone should quickly help us do that, please. The first person that would show that to me, you do it and you quickly snap it and you send it, or if you can, okay, I'm sorry, you may not be able to do that. You can just do the working, simple working on the chat page. You have less than 3 minutes now, please. assignment. I would love that you send it on your Edmodo platform, so that we would at least cover a large amount or large portion of this class today. All right, going to the next slide. That's what I said in the next slide, that you should attempt it. So let's just move on. All right. Now, before we move to the examples of all those the seven types of machine, simple machine, we need to know something, that there is a wide difference between an ideal machine and a real machine, right? An ideal machine, as I've written there, is that kind of machine that is not affected by any form of friction, is not affected by heat. Nothing is affecting it. So it is perfect. That's why we call it. So because it's affected, the efficiency will always be less than 100%, because the work input will be greater than the work output. The much force that you put into it, it is not exactly the same amount of work that will be coming out for you that you expect. So and if you look, is the work output over work input. The moment the work input is more than the work output, that ratio, that fraction will never be up to 1. So by the time you multiply it by 100%, it will not be up to 100%. So you need to take note of that. They usually ask that question in objective, that in an ideal machine or in a real machine, this and that. So you need to simple, as you can see, we have the lever, we have the plane, we have the block tackle. The block and tackle system is a form of pulley, jack and screw, and we have the wedge, right? So let's take each and every one of them. I'm very sure you will enjoy the way I've just designed this slide. It's more interactive. When you have something more like audio, you would not forget very fast. It will stick to your brain. So when we talk about lever, we said lever is the simplest type of machine, and it can overcome large force using a small force. So a lever has three parts. It consists of load, fulcrum, and effort, right? So, and it works on the principle of moment. I hope we all remember the principle of moment, which talks about the moment of force about a point in a clockwise direction equals to the moment of a force about the same point in the anti-clockwise direction. And we know moment is force times distance. So every calculation that you have under lever, if you remember your equilibrium of rigid body under the action of parallel or non-parallel force, where we talk about the principle of moment, you've seen Kroger before. that kind that the carpenter seesaw. We have the scissors, and we even have the oil pump. If you have ever seen oil pump, some of us may not have been there, but if you have ever seen oil pump working when it is going down and up to pump oil, black oil, out from the ground, you will understand that that is that. So it is very important you know the examples of the first order. If you look at all of them, they are all they are all having fulcrum at their middle. Is that clear? Please, while I'm explaining, if there's anything that is not clear to you, you can just write on the chat page. Kindly unmute, mute yourself so that we can all enjoy this conversation. Going back to that, so that's first order. Now let's go to the second order. Going to the second order, you see what we have there. The second order, we have the wheelbarrow, we have the nut cracker, the opener, the bottle opener, the you have seen, some of us may have seen the Hausa lemon seller that they usually squeeze lemon uh, into the liquid of the lemon into the bottle. That's exactly what they are using. So you see that our edge is the fulcrum, right? You see that edge is the fulcrum, this point, and you have the load in the middle, and this your hand is the effort that you are putting into it. I hope that is clear. Please kindly tell me if you are getting what I'm saying on that chat page so that I'll be sure that we are all carried along, please. Right? So the third order is that one in which the effort is in the middle. The effort is in the middle. As you can see, an example is your forceps or your hand, your forehand. We have the broom, we have the shovel, we have the sugar tongue. All these are examples of third order. And the reason they are examples of third order is because effort is actually in the middle of the system of arrangements. Effort is actually in the middle of the system of arrangements. Effort is in the middle. Listen and look at it very well. If anything is not clear, quickly tell me before I move on, please. Quickly tell me before I center at its center, and that seesaw is 5 meter long. So that means you will divide that seesaw into two, so that will be 2.5 on one side and 2.5 on the other side, right? And I said a boy weighing 40 newtons sits at a distance of 1 meter from the fulcrum. So if wow, it said 1 meters from the fulcrum. Um, Actually, what I wanted to say there is 1 meters from the beginning of the plank. Because if you look at the way I drew that diagram, 1 meter from the beginning of the plank is the place I put that diagram. Then the distance of that person from the fulcrum is 1.5. So it's supposed to be a distance of 1 meters from the plank, from the beginning of the plank. So if you have that, they now said that where must a girl weighing 25 newton sit so as to balance the plank? So to balance that plank, you follow that configuration. You are looking at that distance from the fulcrum to where the girl is, we call it X, and the boy, the distance of the boy to the fulcrum is 1.5 meters, because we have said earlier that the plank, the fulcrum is at the center of the plank, so it will have been divided into two. Is that clear? So if it is divided into 2, that is a 2.5. So if the boy is at 1 meters from the beginning of the plank, then the distance from that boy to the fulcrum will now be 1.5. So following the principle of moment, you see what I've just written there, that W boy, the weight of the boy, times the distance from the fulcrum equals to the weight of the girl times the distance from the fulcrum, and we have that. So when I was now giving the comment on the answer, I wrote 2 things, because in your exam, so if it is given, so I said the girl would sit at 2.4 meters away from the fulcrum, or you say that that girl is at 4.9 meters mark of the plank. What I mean by 4.9 meters mark of the plank is, if from the fulcrum, if from here to here is 2.4, as we have seen, and we know that from here down to this place is also what, 2.5. So you just see 2.4 plus 2.5, which is 4.9 from the beginning of that plank. I hope that is clear. So that is what is said there. Going to the next example, we have another example there. The example says, how much force is needed to move a box weighing 400 Newton with a crowbar of length 15 meters if the fulcrum is placed 4 meters from the box? The fulcrum is placed 4 meters from the box. Look at that diagram that I showed there, the real life situation. So that real life situation will make you understand what is actually going on. It will make you understand what is actually going on. You have someone that is using a crowbar tilted. So if you now want to lift it, you have to put a kind of stone or something. That stone will be the fulcrum. So you put it on it, and that's what you use to raise the load. So they are saying that the stone that we are calling the fulcrum here, the fulcrum is now placed 4 meters from that box. So you can see that distance is 4 meters, and the whole crowbar is 15. So what to be the remaining distance? It should be 11. That will be the remaining distance, and there will be, and you follow the same. Of that will be equal to the effort that is applied times the distance of that effort to the pivot. So that is what is there, and that is how the calculation goes. So these are examples of question on that lever. So before I move on to inclined plane, I would like to ask 1 or 2 questions from us. Looking at the previous question here, can someone quickly solve? Listen to the question again. In a seesaw game, a 2 Newton boy is at a distance of 5 meters. A 2 Newton boy is at a distance of 5 meters from the fulcrum. A 2 Newton boy is at a distance of 5 meters from the fulcrum. Where must a plumpy boy of 7 Newton sit to balance on the seesaw? Look at it again. Let me write those parameters. A seesaw game. We have a boy having a weight. The boy has a weight. Let me write it there. So we have the weight of the first boy is 2 Newton, and he is at a distance of 5 meters away from the fulcrum. We now said we have another boy. So I'm now saying, what is the distance that boy must be? At what distance must the boy be to the fulcrum if the seesaw is to balance? Noting that the length of that seesaw, the seesaw is 10 no yes 10 meters long. The length of the seesaw is 10 meters. The length of the seesaw is 10 meters, right? Someone should try that question. Please, I would love to have that response in like a minute or. Now, be reminded that I said in the question I wrote earlier, I made a slight mistake of saying from the fulcrum. It is supposed to be from the beginning of that plank. So if you are solving your own question now that I said 5 meters from the fulcrum, this point that you have 1.5 will now be that 5. That's what you'll be doing in your own question. That point will be 5. Then you'll be looking for this other side that we call like X. So you are just following the same kind of question in another way around. Quickly, what's the answer to that question? Please, you are not supposed to be writing anything. Okay. Someone is just passing the response for the question. 1.42 meter, okay. That should be 10 over 7, right? 10 over 7. Great. So that is clear. Do we have any answer? $1.4 is still okay. We are still so everybody is on the same page. Great. All right. So let me clear all this. So that is that about liver. So if you want to understand or you get this liver question perfectly, just try and I think the second instructor, physics instructor, I've taught you moment of a force. Yes, I was at that class. So it means that anything related to liver, you should be able to do it perfectly. So because of time, let me just quickly rush inclined plane. So when the time is up, we'll continue the next class. So what is an inclined plane? They said an inclined plane is a type of machine that is used to raise heavy loads, such as drum of oil, up a sloping plank to the high floor, okay, high floors of lorries. So if you want to raise something up along that path, it may not be easy for you to carry it on your head and say you want to put it there. Let's say you want to carry a box or a drum of oil from the ground into a lorry. You may not be able to carry it if the lorry is filled with the oil. So you have to use a plank that will be at that slant height, as you can see that I've done over there. And the velocity ratio is written as 1 over sine theta. So that is the formula. Most of the calculation only needed the velocity ratio, most of them. So if you can get the velocity ratio, every other one is very simple. So lastly, let me just show this example. You go and study how the question is. WAEC 1995, question number 4, objective. You see it there. It says a body of mass 7.5 kilograms is to be pulled up along a plane inclined at 30 degrees to the horizontal. if the efficiency of the plane is 75%, what's the minimum force required to pull the body up the plane? So you can see how it has been solved there. So you study it and you understand it. Anything that is not clear, by next week when we continue this class, would address it. Thank you. So I think the admin can open up, they can unmute everybody so that if we have any question or clarification before we call the class off for today. All right. So is there anybody that needs to get some things clear, or it's clear to everybody? I need response, please. Are we all clear with what I've just said?
Please repeat something about work input and work output before.